In the last chapter, we went over normal distributions and talked about all kinds of problems and calculations that we could do with normal distributions that went way beyond the empirical rule and included a lot of the empirical rule as well. In this chapter, we're going to talk specifically about sampling distributions, a special type of distribution. And most of the sampling distributions that we'll use will probably be normal or close enough to normal that we'll be able to do all the same calculations that we did previously, but there will be some adjustments that we'll need to make, some minor adjustments. So this chapter really builds heavily on the previous chapter. And we use the central limit theorem to tell us if we have a normal distribution and if we're allowed to do all of these problems that we will do in this chapter. By the way, this chapter and the previous chapter will be what we use to build our confidence intervals and hypotheses testing in the next couple of chapters. So these chapters are so tightly related here in these few chapters. So this looks familiar, I'm sure. Just like the last chapter, just like the last video, we want to have a process for working these problems. And it says normal distribution problems, and this is the same thing for sampling distribution problems as long as they are normally distributed, and we'll talk about when that is in just a second. But our process for working the problem would be to first draw the normal curve and then label and shade everything that's relevant in the problem and the mean and the minimum and the maximum of the shaded regions and all that jazz. And then the third step is to calculate, and we'll still use NormalCDF and InvNorm for these. There will be a slight tweak in the very last input of NormalCDF and in the very last input of InvNorm because our standard deviation for sampling distributions is very slightly different than our standard deviation on normal population distributions. So on a population distribution, you've got all these x's, and the x represents a single data value. We just call it x because we don't know what that data value is. So all of these x's represent different single data values. When we're doing the sampling distribution, though, so this distribution is the distribution of x's. This distribution is the distribution of x bars, or the sampling distribution of sample means. So here we're going to say, okay, we don't have a single data value. We're going to do a collection of 10 data values, or maybe we'll say 20 data values, or maybe we'll say 100 data values. So we'll decide what the sample size is, and then every single one of these will be that exact same sample size. And we will figure out what the mean of those 10 are, or the mean of those 100 are. And those are going to be our new data values. That's what we're going to plot in our new distribution. And it turns out that when you go from a sample size of 1 to a sample size of 5 and then 10 and then 20, you'll notice that even a uniform distribution gets a little more normal and a little more normal and a little more normal. And even if you started out with some crazy bimodal distribution or some crazy skewed distribution, it turns out the central limit theorem tells us that by the time you get to at least 30 data values or more, you have that kind of this magical guarantee almost that your distribution will be close enough to normal that we can do all the magical things we did in the previous chapter, like NormalCDF and InvNorm and computing the z-score and all that wonderful stuff. And this textbook on page 401 describes a little bit about how our distribution of x bars is actually going to be, according to the central limit theorem, as long as we get a large enough sample size. Also, you could have a tiny sample size, and if the original distribution was a normal distribution. So, like, if you're talking about height of college-age students by gender, that actually is a normal distribution. So even if you had a sample of size 2 or 5, or however many, it wouldn't matter, because if you start out normal, you're going to stay normal. So really there are two ways a sampling distribution can be normal. Number one, they started out that way, or number two, you've got at least 30 data values or more, like the central limit theorem says. And then when that happens, your mean of the x bars happens to be exactly the same thing that it started as. So it's just the population mean. So it works out really nice that way. But we have to tweak the standard deviation, because the standard deviation for the x bar distribution, you have to take the population standard deviation and divide it by the square root of n. So you'll notice like the normal CDF is exactly the same inputs on the first three that we've always had. The lower limit of the shaded area, the upper limit of the shaded area, the mean, and then the fourth input starts out the same, standard deviation, but now we take that population standard deviation and we divide it by the square root of our sample size, or the square root of n, if you will. The z-score is also similarly altered. Instead of a single data value of x, we now have x bar that represents the sample, a single sample mean value, and then this mu x, that's just mu, and then sigma x is just sigma as well, and so that's sigma divided by the square root of n. So the thing that changes the most here, since this mean stays the same and x changes to x bar, but the thing that changes the most here is that our denominator now gets divided by the square root of n. So definitely don't forget to divide by that square root of n. You'll be doing that a lot in this chapter. And then we go through the same process. We draw the normal curve if we know we have a normal distribution, which we probably will know. And then next we will label and shade. So we'll label the mean of our distribution, we'll label negative and positive infinity, and we'll label everything that we're given in the problem, especially when it relates to where to shade and what the relevant regions are for the problem. And then our third step is the same. We will calculate. We will choose based on whether what we want is above the belt in orange, we'll choose normal CDF, or below the belt in blue, we'll choose inverse norm, and we have exactly the same inputs, except for our standard deviation is now for the sampling distribution. And so that will be this population standard deviation divided by the square root of n. And then we'll use the same sort of scenario, but now we have a sample size of 32. So that's like all the students in one term averaged together. We'll still assume that our population mean is 77.5. We'll assume that our population standard deviation is 11.5, and we'll have a sample size of 32. And then we can go and work a problem. Notice that our mean is 77.5. Now our standard deviation, whether we're doing normal CDF or inverse norm, or the z-score, or just answering the question about the standard deviation, it's always going to be sigma divided by the square root of n. So we've got our population standard deviation of 11.5, and then we're dividing it by the square root of 32, which is our sample size. And then our question asks us the probability that we will have a randomly selected sample, not just a single data value, but an entire sample of 32 people, and whose average will be below a C, so 70 or below. And so that means we're going to use normal CDF to compute. And so because we're above the belt, that's why we're using normal CDF. Our minimum of our shaded region is negative 1E99. By the way, this is the negative symbol, this is a minus symbol. If you use minus 1E99, you may get an error. So negative 1, and then second comma, for our E, and then 99, and then 70, and then 77.5. And then I'm just going to put 11.5 divided by square root of 32 right in here as our standard deviation. Square root is second, and then right here, the square root key. And then 32, and I'm going to close my parenthesis and go down and paste. And this is, the E is scientific notation. So this E with positive 99 means that you would take the understood decimal that's right here. So -1 is the same thing as -1.0, for instance. So you take the understood decimal here, and this says move it 99 in the positive direction or to the right. So we would move it 99 spaces to the right. So it would be -1 followed by 99 zeros, and then you'd have a decimal. Here, though, for our answer, what this is saying is that we would have this decimal move to the left because it's negative 4 spaces. So move it to the left once, and then you'll put 3 zeros. So you'd have 0 point, and then 3 zeros, and then 1, 1, 2 would be your answer here. As a matter of fact, even if we were only asked to find probability here. So our answer here would be 0.000112. But if we had been asked for percentage, that would still be really small. So if we were asked for percentage, we would multiply by 100%. That's still not even 1% or 0.1%, it's 0.01%. So this is a tiny, tiny, tiny probability if all of our assumptions hold true. And then we have a slightly different scenario. Still, we have the selected sample of 32. Here, our randomly selected sample is going to be less than 40% of other randomly selected samples. So it's going to be less than 40%, but it's going to be more than 60%. So less than 40, so this value is less than 40%, but it's more than 60%. And so that would mean it would be right here. Inverse norm is what we want to find a data value, and because it's labeled below, something we would label below, and just by where it's labeled, we should expect something to be more than 77.5. And then 1 minus 0.40, because area to the left is equal to 1 minus area to the right. That'll give us the 60%, or 0.60. So 40% here, 60% here, 0.60 here. And then our mean, and now our standard deviation divided by the square root of n. And we're going to use inverse norm. So second DISTR 3. And then we can literally type in 1 minus 0.40 if we wanted to, and 77.5, and 11.5 divided by the square root of 32. And so we did get something a little bit more than 77.5. We got 78.015. And so the score that would be less than 40% of all of our other selected samples would be an average of 78.02. And so that's how we can work some Chapter 7 problems. Hopefully that will help.